In this video, we're going to look at the conservation of angular momentum. One of the consequences of this is we can sort of answer the question, why do helicopters have tail rotors? Why do you need that extra little propeller on the back? And this has to do with conservation of momentum, right? You're spinning one thing in one direction, and if you change that, you're going to cause the other thing to spin in the other direction. More on that as we go. So we're going to look at stating implying the law of conservation of angular momentum, and it has two kind of pieces. The first is the condition under which it is met. That is that the net external torques have to be equal to zero. And that should remind you of our criteria for linear momentum conservation. Net external force needed to be zero. If that is true, then the angular momentum of the system before and after, or at two different points in time, will be equal. So angular momentum will be conserved. Some of the kind of Newton's second law relationships with regards to this, right? If you remember last time I talked about in momentum, we say if the net external force is equal to the change in momentum over time, because that's force times time equals change in momentum, right? Impulse equals change in momentum. And the related idea here is that the net external torque is equal to the change in angular momentum over time, or the rate of change, like that. So when we think about a system, this is a classic example of a person on a rotating platform or surface with some amount of mass in their hands, and they can move it in and out. Well, what will happen here is that moving the masses in and out will change the moment of inertia of the system. And since there's no net external torques, right, the system includes the platform and the person and the things they're holding, then we should expect the angular momentum to stay the same. But if you can change moment of inertia, then you also have to see a subsequent change in angular velocity to balance that out, right? So if you bring in those masses, then the angular velocity will increase because you've decreased the moment of inertia. And if you bring that back out again, you can slow it down. Now, the question is if energy is conserved, right? We saw that in linear momentum, that in certain cases, energy and momentum were conserved. Well, if you think about this situation, we find that the only type of energy that is involved would be rotational kinetic energy, because it's not translating, and certainly we don't have any gravitational potential or spring potential to deal with here. But as it turns out, the kinetic energy increases as you bring in those masses. And that's because angular momentum depends on I omega. And if you decrease I, omega goes up proportionally. But of course, kinetic energy depends on I and omega squared. And so if you were to have conservation of that quantity, you couldn't have conservation of angular momentum. The reason for this is that you are doing work to cause those masses to move inward. And that changes, and that's non-conservative work, so it will actually change the angular, the rotational kinetic energy. It will increase it. Another consequence of this is a gyroscope. If you've ever played with a gyroscope, you know that you can get them spinning, and then once they're spinning, it's really hard to change their rotation. They kind of hold that, and that is used for navigation and all sorts of other interesting things. But if the wheel doesn't spin, and the classic large-scale example of this is you take like a bike wheel, you get it spinning, and you attach it to a pole, and you can hold it, and it will stay upright. And when it has angular momentum, since that quantity is conserved, if you apply a net external torque to it, then the rotation will shift to counteract that change. So I've got a little video here. This is from MIT lab. We've watched the push me, pull you back with linear momentum, so same kind of idea. But here's that bicycle wheel hanging from a rope, right? Just sort of hanging there. And if you get it spinning, which is what this person is doing right now, get it spinning really, really fast, and then you sort of get it set and hang it there, it will stay upright, but it will start to precess, right? Rotate. And that's because as gravity tries to straighten that out, it's changing the angular momentum of the spinning wheel. And so the whole system is going to rotate to try to conserve angular momentum as it goes. Now, obviously, there are non-conservative forces here, and everything will eventually slow down, but that is the basic idea, right, as it loses its energy. Another thing we could investigate is, what if you were to take that same wheel and hold it while on a rotating platform? So this is a person sitting on a chair with a bicycle wheel and the gyroscope. And if you were to hold it, so it's spinning clockwise or say clockwise, and then you were to flip it over, suddenly you would have changed the direction of the angular momentum dramatically, flipped the direction. And if you do that, then what you end up with is a situation where the whole platform will start to rotate to conserve angular momentum. And so I've got another video here for you that I'll let you just kind of watch and listen to.
When I hold the spinning wheel, nothing crazy happens. When I flip it, I spin. Back, and I stop. Flip it, I spin. So the question is, why am I spinning? So I have to force the wheel to turn over. Now Newton's third law says that for every force, there's an equal and opposite force acting as well. So when I force the wheel is applying a force equal and opposite onto me, causing me to turn. So the same thing applies when I'm on the ground, but the friction between my shoes and the ground stop me from spinning. So another way to explain what's going on is through conservation of angular momentum. Now, angular momentum is something that tells you how hard it is to either start or stop something from spinning. And it depends on two things. One, how fast it's spinning. We call that the angular frequency. Two, its shape, or what we call the moment of inertia. So this wheel is rotating counterclockwise. Now I'm going to teach you a trick. So get your right hand. I want you to curl your fingers in a counterclockwise direction. And you see that your thumb is pointing upwards. We'll call that the positive direction. So see, this wheel has positive angular momentum with a magnitude of L. Angular momentum is conserved. That means, as long as there are no outside forces, the total angular momentum of the system always stays the same. So when you flip this thing over and do the right hand trick, your thumb points down, or in the negative direction. So the angular momentum of this wheel is now negative. So the whole system, me, the turntable, and the wheel starts out at negative L. But when you flip the wheel now has positive L. So the whole system needs to stay at negative L because of conservation of angular momentum. So I need to spin with angular momentum of negative 2L. That's why I spin the other way.
All right. So hopefully that was a good explanation for you of how this whole thing works.
Nothing crazy happens.
Right? When we're talking about angular momentum, right, we are talking about basically with the direction either up or down, right, clockwise or counterclockwise. And if you change the angular momentum of one aspect of the system will react to conserve angular momentum. As long as that is an internal change, right? As we saw the person there flipping the wheel over, that wasn't someone coming from the outside and flipping it over and handing it back. In that case, they would not have spun at all. So let's look at an example or two. If you have two masses at the end of a rod, right, we have a moment of inertia of 2mr squared, which is a relatively straightforward situation. The r that we have, right, and if we were to lower that distance, make it to r over 2, maybe we fold up those arms, what would happen to the angular momentum? Well, angular momentum should be conserved as long as this can be done internally, right? I omega equals I prime omega prime. And actually, let me pause there. Unlike linear momentum, where the mass really isn't something we could change, we could have one mass and another mass and have them either stick together or bounce off of each other. But the mass in the system can't change. In this case, angular momentum, right, which is made up of moment of inertia and angular velocity, both terms, the angular velocity and the moment of inertia, can actually change, because moment of inertia changing is not getting rid of or adding mass, which we can't do. It is just moving it around, redistributing it, changing the r value. So we have 2m r squared omega initially, and at the end we have 2m r over 2 quantity squared omega prime. A lot of this stuff cancels out, right? The 2m's, the r squareds, and we are left with a factor of 2 in there, which means omega prime is, or 2 squared, so 4 omega. And if we started at 10 radians per second, we're now at 40 radians per second. Another example for you, a particle of mass m collides and sticks to a long, thin rod of mass m. The 1 meter long rod pivots freely about a central horizontal axis. What is omega final when the rod is vertical? Now, this is a two-part problem. We start with a collision between the mass that is a small point particle and the mass that is a rod, and then they stick together and start to move. Now, that sounds hopefully a lot like the kind of momentum problem we solve for in linear momentum. Then it's going to swing down to the vertical, and that is a conservation of energy problem. So for collisions and explosions, we're still going to use the conservation of momentum, just like the linear momentum we did before. So the first event is, I'll move myself out of the way. The origin can be at the pivot, so the unknown pivot forces do not exert any torque, and we don't have to worry about them. So we'll pivot around the central axis, and we look at the system as shown. We say the angular momentum should be conserved because in the instant of that collision, there's no net external torques that we need to worry about. So the L over 2, which is the distance, times mv, so that's your angular momentum of the single point particle that's going to hit, should be equal to the total moment of inertia times omega final. And for the rod, that's 1/12 ml squared, and for the ball, that's m times L over 2 squared. We can simplify this equation, cancel out some things that go away, and we end up with omega prime, the angular momentum or angular velocity after, is 3v times L, or divided by L over 2. Right? And if we plug in the information, 5 meters per second and 1 meter, we end up with our final results, 7.5 radians per second, just after the collision. So now we have information that we can use to put into our conservation of energy event. This is while it swings downward. We start with some rotational kinetic energy. This is basically falling chimney territory. The axis is not moving, but we are rotating, and we have some gravitational potential, and later we get rotational at the end. At the beginning, we have 1/2 I omega prime squared. That's that omega prime from the previous part of the problem, plus mg L over 2. The reason for that is the rod itself, it is not changing height, so it doesn't have any gravitational potential energy, or at least no change. The ball will swing from a height of L over 2 to 0, or a height of where it started to L over 2 below. And then at the end, we have 1/2 I omega final squared. Right? We can cancel out these factors of 1/2, and we can solve for omega final. Right? We need to plug in some various values here, and we end up with 9.25 radians per second. So, which is faster than it was going after the collision, because the gravitational potential energy gets converted to kinetic. This is important. There can be external forces, but they cannot exert a torque during our collision, right? So although there are external forces on this system, during the collision, they don't affect our result at all. So a couple of more examples. I've got another video here, angular momentum in space. So we've got a little video here, astronaut on the International Space Station talking about angular momentum and the giant gyroscope that keeps the space station from tumbling around instead of using fuel to adjust its orbit. I'll let you take a look at this video on your own time because it is a little bit longer and you'll be able to hear it better. But that's the end. All right, we'll talk a little bit more about this stuff in class.